couple lectures ago, we were talking about chemical reactions. And we had this written up on the board. That is A plus B gives you AB. So this is an example of a reaction that is anabolic and it's endergonic. That means that, of course, it's requiring energy. That energy should be stored in the bonds of the creation of that molecule, and it's a building process. Now, there's a couple of things about chemical reactions that we haven't talked about. So if it's requiring energy, where does that energy come from? So all cells, and in fact all life, uses a molecule called ATP. You might recall that this is a nucleic acid. Nucleic acids are made of sugars, nitrogen base group, and a phosphate group. So in this case, ATP looks like this, okay? So this is a typical nucleotide. In this case, though, it's got 3 phosphate groups, and the bonds between these phosphate groups are what they call high energy bonds, including the bond that is between the last phosphate and the actual sugar molecule. Now, anytime you break off one of these phosphate groups, you're going to release energy, and that energy can go directly into a system. So oftentimes they'll draw it like this. That is, they'll say ATP gives energy to the system, and it becomes ADP plus PI. So let's just talk about what that means. Okay, so adenosine triphosphate is the name of ATP. 3 phosphates, triphosphate, adenosine triphosphate. Now, when it breaks that phosphate group off, then it becomes adenosine diphosphate, or ADP, and the phosphate group then is going to be free floating, and it's what they call an inorganic phosphate because it's no longer attached to an organic molecule, so it's called PI. And this is going to then provide energy, that energy then would be going directly into this system. So that's implied. Now, another thing about this that we haven't said is that how much energy are we talking? So the energy provided by ATP is, for one phosphate group breaking off, is 7 kilocalories of energy. That's like a kilocal is a big C calorie. And so you get 7 calories of energy. And 7 kilocalories, 7 kilocalories of energy. And so what's going to happen is that you are going to, a lot of these reactions wouldn't require, let's say, for example, 7. Let's say this reaction costs 6 kilocalories of energy. In other words, to make AB the product. So what happens to the leftovers? So the leftover energy is going to come out of the system as heat. And oftentimes they will draw, I just forgot to draw. They're going to draw it with a little symbol like that. So that that symbol means that it lost heat. This is why you're warm, because a lot of chemical reactions that happen within your cell are going to lose some heat energy during the process, because things don't just cost 7 kilocalories or 14 kilocalories or any multiple of 7. So there's going to be some energy loss. Now that energy loss is not necessarily lost. It could be used to drive another system. This is called energy coupling, and I'll show you an overhead on that in a little bit. Okay, so energy is provided by this ATP molecule, usually by breaking off the first phosphate group, and that provides this energy. You can also, let me show you this other one. You can also have a reaction like this one where you're breaking a molecule down. So this would be what type of reaction? If I'm breaking down, that would be catabolic. And catabolic releases energy. That energy release could make ATP. So looking at this, energy from catabolism would then make ATP. Energy for, I don't know why they didn't say anabolism over here, so energy to do cellular work, would then use that energy from the ATP, making ADP and PI. Okay, so that's the basic way that goes. Now, if you have a system like this one, either system, it doesn't really matter, but let's just look at this one again. If you have a system like this one, and I wanted to make it happen faster, I might have the energy available and so forth, but I want it to happen in a significant way. For example, if I were to put salt in water and I wanted salt water, and I wanted it fairly fast, what would I do to speed that up? So the things that I would normally do are, I'm going to provide a catalyst, and this catalyst is usually heating or stirring, right? In the lab, I would put it on a hot plate, or I might put a stirrer in there, or I might do both, and that's going to give me that salt water very, very quickly, and that's going to speed up my chemical reaction. Okay, so this is the speed of a chemical reaction is making things happen at a significant timeline. In other words, if I need salt water right now, then I want to make it fast. Okay, so if I wanted AB right now to have something else happen within the cell, I'm going to have to speed that up. But in biological systems, you can't use heat. Why not? Because remember, hydrogen bonds and in fact ionic associations are broken down, which are a lot of molecules will be broken apart by that action, right? So I can't heat it up and I can't really stir it up. So I'm going to have to use some other kind of catalyst. So this catalyst in biological systems is called an enzyme. Enzymes are globular proteins. They're three-dimensional structures. We've kind of alluded to them before. And what an enzyme, being a three-dimensional structure, is a molecule that is going to grab the substrate molecules. Grab the reactants. In this case, they are going to be called substrate when they're interacting with the enzyme. They're going to grab these guys and help them come together. As long as the energy is present, they will come together easily. So what the enzyme does is it's going to speed up the association of A and B. Just like in the salt water, it's speeding up the association of water molecules around the individual ions of sodium and chloride to dissolve salt in the water. So this is speeding up this association. So I just drew a little diagram here. E for enzyme. And it would have, in this case, a binding site for A and a binding site for B. All right? So it's a binding site for the reactants. Now, if it's interacting with an enzyme, it's called a substrate. So A and B become substrate molecules as they're interacting with that enzyme. And when they are all joined together, in other words, the enzyme has both A and B in it, it's called the enzyme substrate complex. Now, enzymes can act in different ways. Sometimes they can change shape to make A and B come close together. Maybe binding site A has to be filled before binding site B, etc. There's different ways that enzymes work, and we'll talk a little bit about that later. But anyway, the enzyme is going to help the association of A plus B. Then all I have to do in this case is provide the energy. And what do I have? I have AB as a molecule. And the enzyme then would be left to go do it to another reaction. That is, it would be left to do this reaction again, because presumably in the cell, I want a lot of AB. All right, that's kind of the point. Now, enzymes can also work the other way. In other words, when I have a catabolic reaction and I'm losing energy, I need to break AB apart. So I may have an enzyme that has a binding, it's not an E in this case, has a binding site for AB, and then it's going to allow A and B to disassociate. So you have enzymes for both directions of the chemical reaction.